Hi everyone, this is Bill Stubbs. Welcome to the fourth video in my series, Dissecting the Standard Model of Particle Physics, entitled Return of the Electrons. In this video, I continue discussing the contents of my book, Three Quarks Missed the Mark, by examining the HERA F2 data and showing how it leads to the discovery of electrons inside the pions forming the proton. Let's get started. In the last video, we saw that a complete set of low Q-squared proton F2 data indicates that the proton is made of 8 or 9 component particles. If these particles are spin 1/2 particles, as initially concluded by the MIT SLAC team, they are probably muons. However, a strong argument was made for the particles being spin 0 particles, which would make pions the likely proton components. Consequently, pions are the assumed proton components going forward. In light of this, the question arises, what is the high Q-squared HERA data telling us? The table shown gives the F2 values for HERA deep inelastic scattering runs performed in 1993 as a function of the momentum fraction x and the momentum transfer Q-squared. The F2 values for a given x value are relatively constant over Q-squared ranges from a few GeV squared to several hundred GeV squared, which indicates that scaling is in play. Because of this, it seems reasonable to reduce the F2 data for a given x value by taking the average of the F2 values available for that x, with the 3 exceptions shown to smooth the curve. The F2 values given in the far right column of the table are the average values. This table shows the raw JLab F2 data for a given x, the average F2 value for that x, and a crude attempt to extract scaled F2 values for each x using the raw data in bold italics for the x. When the JLab and HERA values are combined with the SLAC data, they produce a curve like this. In this graph, 645 SLAC F2 values are smooth using a 20-point moving average as a function of x, and the JLab F2 values are fit with a fourth-order polynomial. The graph shows that at about x equals 0.125, all 3 devices see essentially the same F2 value. They all see a proton component particle with about 1/8 the proton's momentum. But as x approaches 0, the HERA F2 curve rises sharply. This graph of the same F2 data, but with a logarithmic x-axis, shows that between x equals 0 and 0.133, the curve takes the shape of the combined SLAC JLab proton F2 curve for x between 0.05 and 1. It appears HERA has produced an F2 curve for a particle other than the proton, apparently for the component particles of the proton, pions. HERA is looking inside the component particles of the proton and seeing even smaller particles than the pions. HERA is seeing the particles that make up the pions. The graph shows that the HERA F2 curve peaks between x equals 0.0005 and x equals 0.0006, which suggests that the proton contains between 1,600 and 2,000 of these smaller particles. If there are 8 pions in the proton, that means that the pions contain between 200 and 250 of the smaller particles. Based on the shape of the HERA proton F2 curve, it is the F2 curve of the proton component particles, the pions, stacked on top of the proton F2 curve. This curve can be isolated and analyzed to determine the structure of the pions. To do this, we must first convert the proton F2 curve into a pion F2 curve. The proton F2 data is converted to pion F2 data by first converting the proton momentum fractions to pion momentum fractions by multiplying them by 8, then by converting the proton F2 values to pion F2 values by subtracting 0.36 from them. A table of the HERA proton F2 data is shown with the conversions to the pion F2 data. Since it appears the proton is 8 pions, its mass is 8 times the pion's mass. Therefore, a particle carrying a given fraction of the proton's momentum is carrying 8 times that fraction of the pion's momentum. The momentum fraction conversion is easily reflected on the HERA proton F2 graph. Just multiply the graduations of the proton momentum fraction axis by 8 without altering the curve on the graph, as shown by the values underneath the proton values on the x-axis. Now, the proton momentum fraction of x equals 0.125 becomes x equals 1.0 for the pion. It represents a whole pion, and all of the graduations along the x-axis now scale to conform to the fraction of the pion's momentum they correspond to. The placement of the data points on the graph is unaltered. They now just align with the higher momentum fractions of the particles HERA is probing, the pions. The conversion of the proton F2 values to pion F2 values comes from recognizing that the F2 value of a whole particle, that is, at its x equal 1, is 0. The pion's x equal 1 is the proton's x equals 0.125. At this x, the proton's peak F2 value as a result of the pions forming it appears. Surveying the slack proton F2 values in the vicinity of x equals 0.125 reveals that the peak F2 is about 0.36. This means that the proton's F2 equals 0.36 is the pion's F2 equals 0. The simplest way to make this conversion is just to subtract 0.36 from the proton's F2 value at x equals 0.125. Applying this conversion to all the proton F2 values between x equals 0 and 0.125 just shifts the proton F2 curve down by 0.36. It is the same as subtracting 0.36 from the values of the F2 axis graduations on the proton F2 graph, as shown. Again, the placement of the points on the graph does not change, only the scale of the F2 axis of the graph. The resulting HERA pion F2 curve is shown. With it, we can now analyze the structure of the pions making up the proton. To do this, we must determine at what x value the pion F2 peaks. Now showing is the pion F2 curve for x between 0 and 0.1. This graph zooms in on the pion peak F2 value. The data points have been broken into two segments. One, the triangles, where the F2 rises to the peak as x increases from x equals 0, and the other, the dots, where the F2 falls towards 0 as x approaches 1. Each segment is fitted with a logarithmic fit as shown. We can get a good approximation of where the peak F2 occurs by assuming the two fits intersect near the peak. Therefore, setting the fits equal and solving for x should give us our approximation. The x value where the two fits meet is x equals 0.004418. The reciprocal of this is 226.3, which means that, on average, the pions in the proton appear to contain about 226.3 particles. A proton made of 8 of these pions would contain 1,810 particles. This makes the particles inside the pions appear to likely be electrons and positrons. It is just 26 particles short of the number of free electron masses, 1,836, that is the mass of the proton. However, for the proton to have a positive charge, there must be one more positron than electron in it, making the total number of particles in it odd. Pions with an average of 229.625 particles, an x of 0.004355, would produce a proton with 1,837 particles. This x is just 0.000063 or 1.45% less than our approximation. Therefore, We will now assume that x equals 0.004355 is where the pion's peak F sub 2 value occurs. So, it appears the pion, and by extension the proton, is made of electrons and positrons. But how is this possible? The original electron-proton deep inelastic scattering analyses concluded that the proton is made of 3 valence quarks, 2 up quarks and 1 down quark, in a sea of up, down, and strange quark-antiquark pairs, all held together by a collection of gluons. The analyses here of the SLAC, JLab, and HERA data in concert appear to reveal that the proton is made of pions, which, in turn, are made of electrons. A question that comes to mind is, how do all these pieces, the pions and the electrons, come together to form the proton? The answer to this question lies, once again, in the F sub 2 structure function curves. Starting with the pions, the F sub 2 curve has a very sharp peak whose value is in the vicinity of 1. According to parton theory, the sharp peak with a value near 1 indicates that the particles the probing electrons encounter within the pion, the electrons and positrons, do not interact strongly with each other. This means that they are likely not bound together like the nucleons within a nucleus, but exist in orbitals like the electrons surrounding the nucleus of an atom. It seems, somehow, a collection of electrons and positrons come together in orbitals to form the structure of the pions. The proton F sub 2 curve is almost diametrically opposite the pion curve structure-wise. Its peak is blunt and has a value much less than 1. This behavior signals that the pions, the SLAC and JLab electrons found inside the proton, interact strongly. They likely do bind together similar to the way protons and neutrons do within a nucleus. Given the apparent structure of the pions, having orbitals containing electrons and positrons, the pions probably bind together by sharing the electrons and positrons between themselves, similar to covalent bonds atoms form in molecules by sharing electrons. This happens to fill deficits they experience as a result of colliding with each other. This would explain why 8 pions, 7 made of roughly 273 electrons and positrons, and 1 of 264, come together to form a proton that is only 1,837 electrons and positrons, 338 fewer particles. During a collision that binds 2 of them, electrons and positrons are lost in each pion due to electrons and positrons from the colliding pions annihilating each other. For example, if the 8 pions form 2 clusters of 4 pions within the proton, then each cluster would form 6 bonds between the 4 pions. The 2 clusters would form a total of 12 bonds between the 8 pions. If the bonds formed when, during the collision that formed them, each of the colliding pions lost 13 electrons and positrons to annihilation, then compensated for the loss through sharing 13 of the other pions' electrons and positrons, each bond represents the 2 pions sharing 26 electrons and positrons, and the 12 bonds a total deficit of 312 electrons and positrons. Then, if a final bond sharing 26 electrons and positrons bound the 2 clusters together, the total electron-positron deficit is 338, and the resulting pion cluster contains 1,837 electrons and positrons. The 2 clusters may form independent of each other and collide to form the proton. Each cluster would have a mass similar to that of a kaon. This is only one scenario that could produce a proton from 8 pions. Several others are possible. So, the new proton model is 8 pions bound together into 2 clusters of 4, with each pion sharing some number of electrons and positrons with each neighbor to form a bond, with the clusters also bound together by sharing electrons and positrons. In the next video, I will show why this model essentially eliminates the need for quarks in baryons and mesons.